Hello again, everyone. As promised, we're at part 3 of carbon dioxide and oxygen calculations. So I'm going back to this same slide, if you want to call it that. And as a reminder, when we look at oxygen content, we're talking about adding the saturation of oxygen, which is about 95 to 99% of the total oxygen that's within the blood. And we're going to add that to the remainder 1 to 5%, which is in the plasma, as it exists as PO2. All right. Here in the pulmonary capillary, if we add the total oxygen saturation, which again is 100%, and the total amount of oxygen that exists as a partial pressure, which should be the same as the alveolar oxygen of 100 torr, we add those two together, we can look at the content of pulmonary capillary oxygen. Moving forward, the arterial oxygen content, again, is looking at the saturation plus the partial pressure. And then when I move up to the venous gas, the mixed venous gas in the pulmonary artery, the CVO2, venous oxygen content, is derived from adding saturation with partial pressure. All right. I've actually got the equations written here, and this is something that we'll actually practice in an upcoming unit with actual values. But here we can learn the formulas. CCO2 is the amount of hemoglobin times 1.34, which is a constant, times the saturation of CO2, pulmonary capillary O2. So if I take the hemoglobin, 1.34, and then the saturation, this is looking at the total amount of oxygen that's riding on that red blood cell in the hemoglobin molecule. Again, that's not all of the oxygen. The remainder is in the plasma of the blood exerted as a partial pressure. So to determine that value, I need to take the P big AO2, which is the alveolar air equation, which is what's determining the partial pressure. And I'm going to take that value and I'm going to multiply it by 0.003. So essentially what I've done is taken the total amount of oxygen that's riding within that red blood cell and added to it the total amount of oxygen that's dissolved in plasma existing as a partial pressure. And when I add these two together, I'll get the total oxygen content in the pulmonary capillary blood. It's easy to determine CaO2 and CVO2 because we're using basically the same formula structure. For the oxygen content in arterial blood, I'm still taking the same hemoglobin, the same the same constant of 1.34, but since we're looking at arterial oxygen content, I'm going to take arterial oxygen saturation. This is the total amount riding within that red blood cell, so I need to also add to it the amount in plasma, which exists as the P little ao2, and again you see we're multiplying by 0.003. So if I take what's within the red blood cell and add to it what's in the plasma, both of those added together gives me the total content. Then for CVO2, oxygen content in venous blood, taking the same hemoglobin, same constant, and instead I'm multiplying it by SVO2, which remember is 75% under normal conditions. This isn't all of it, this is most of it that's within the red blood cell, but we also have to account for what's in the plasma. So we take a PVO2, which is about 40 torr, normal circumstances, multiplied by 0.003. So if you can familiarize yourself with these equations, it'll help you in the subsequent unit. Some ways that we can actually use this information is really cool. Here, as a quick example, I've got QS over QT. QS over QT means shunted cardiac output. So this is actually one of the shunt equations we can use. It's pretty simple because it only has three variables: CCO2, CaO2, and CVO2. So if I can solve these three equations, I can determine shunt. Shunt's an oxygenation problem, so it's no surprise that we're using oxygen formulas to determine shunt. So shunt again is CCO2 minus CaO2 in the numerator over CCO2 minus CVO2 in the denominator. And we'll practice that in a subsequent unit. Also using the formulas, I can determine the delivery of oxygen. To deliver oxygen to the systemic capillary bed, well, to deliver it, I have to have flow of blood, which is cardiac output. And what I'm flowing is this CaO2, which we've determined. So if I take cardiac output and multiply it by the CaO2, I throw in a constant of 10, and I multiply these three values together, I can determine the delivered oxygen to the tissues. Here at the site of the tissues, we can determine respiratory quotient, which is should be the same as the R factor that we used in the P big AO2 equation. Your respiratory quotient is the amount of carbon dioxide that is produced in the tissue bed here in the systemic capillaries divided by the amount of oxygen that's consumed. So a normal VCO2 is approximately 200 mils per minute with a normal VO2 of 250 mils per minute. 200 divided by 250 is what gives us that RQ of 0.8, which is what we used as the respiratory exchange ratio in the alveolar air equation. Taking some normal values, CaO2 of 20, a CVO2 of 15, vols percent, and we'll talk about what volume percent means in our subsequent unit. But just looking at these values, if I have a CaO2 being delivered of 20, and then I have a CVO2 of 15 that's leaving, that means that CaO2 minus CVO2, which is 5, is the amount that was consumed by the tissues. And again, if we take 5 over the initial amount of 20, we see that 25% being used that we refer to up here as this SVO2. If I take the CaO2 and subtract the CVO2 to find the difference, I'm solving for this right here, CaO2 minus CVO2. That's the AVO2 content difference. And again, that difference is telling us how much oxygen was actually consumed by the tissues. So a little bit more formally, I can express that in this equation here, which is called the oxygen extraction ratio. To extract means to take, and a ratio is looking at a fraction. So the extraction ratio of oxygen here by the tissues is set up simply by taking the CaVO2 content difference here, which is normally 5, and putting it over the C by the tissues, 25%. Over here I have a way to determine oxygen consumption, which is the AVO2 content difference times the cardiac output times that constant of 10 that we talked about earlier from here. We can do the quick math. We know that this is 5, cardiac output is 5, 5 times 5 is 25, 25 times 10 is the 250 that we see here. There are many different calculations for VCO2. Here I wrote minute ventilation times the fraction of expired CO2. Some formulas use alveolar ventilation times the fraction of alveolar CO2. These are just condensed versions. The longer versions are about half a page long. We'll actually look at those in a subsequent unit. But when we do the math, you'll get the 200 mils for the CO2 divided by the 250. I think that's all that I have on this particular slide. It's got a lot of equations on it, but ultimately by this point I'll have this in Canvas for you. This is a sheet that has actually all the equations that we've looked at on one sheet of paper. So I hope this helps as a review. If you have any questions, please let me know. Thank you.